Hello, everyone, and thank you very much for this opportunity to present at this journal club today. I will present some results from two different papers led by myself and Eric Jensen, and that I gathered under this title on the influence of atmospheric waves on tropical cirrus clouds. So I want first to take a moment to acknowledge the contributions of my co-authors, Bernd, Eric, Thomas, and Aurélien. And I would like to start this presentation with a few slides introducing the context of our studies. We focus on thin cirrus clouds that form near the top of the tropical tropos layer, or TTL, that I highlighted in yellow on my two figures. So the TTL is the transition region between the troposphere and the stratosphere, as you know. It acts as a getaway between these two regions as air entering the stratosphere is transported upward through the tropical branch of the Boer-Dobson circulation that I represented on the right on my slide. And among the species that are transported in the TTL, water vapor, as you know, is of particular interest because it's a powerful greenhouse gas. So we know that its stratospheric concentration is largely controlled by processes occurring near the cold point tropopause. As the air ascends to these very cool temperatures, water vapor can freeze into ice crystals, which may sediment and dry the parcels before it enters the stratosphere. So the resulting cirrus clouds have two important climatic effects. First, they influence the amount of water vapor that reaches the stratosphere, and second, their large spatial coverage gives them a non-negligible impact on Earth's radiation budget. So we know that cirrus clouds are most frequently observed near the cold point tropopause, where temperature reached their minimum values at around 17 kilometers of altitude. And at these low temperatures, even small fluctuations of a few Kelvin can strongly affect ice crystal growth and sublimation. And we know that temperatures in the TTL are continuously modulated by a broad spectrum of atmospheric waves. On the large scales, I show on the right part of my slide a spectrum. We can see the Kelvin waves, equatorial Rossby waves, mixed Rossby gravity waves, and inertia gravity waves that have periods ranging from a few days to several weeks. And then at smaller scale that I did on top of this spectrum, we have our gravity waves, higher frequency gravity waves that are mostly generated by convection and which produce fluctuations with periods of minutes to hours. So as a result, these cirrus clouds in this region evolve under the combined influence of both large-scale and small-scale temperature variability. So several observational studies have shown that atmospheric waves play a central role in shaping the TTL cirrus. For example, at larger scales, Kim et al. 2016 found that tropical cirrus preferentially occur within the wave-induced cold anomalies. At smaller scales, Chang et Lecuyer showed that cirrus are observed more frequently during the cooling phase of gravity waves, not just cold, but cooling. And finally, Kim and Alexander in 2015 demonstrated that gravity waves can significantly lower the cold point tropopause temperatures, directly influencing the likelihood of cirrus formation and also influencing the stratospheric water vapor. And then, so that was at larger scales, and then at smaller scales, several modeling studies have showed that gravity waves affect the microphysical properties of the clouds. For example, Jensen et al. In 2016 showed that high-frequency fluctuations enhance cooling rates and therefore lead to larger ice crystal concentrations. Dean et al. Demonstrated that temperature fluctuation during a cooling can dominate the properties of these newly formed clouds. And then more recently, we showed with a simple model that including gravity wave variability can significantly improve agreements between our modeled results and observed cirrus microphysics. So all of these studies indicate that gravity waves are a key component of TTL cirrus formation and evolution, but in my knowledge, less is known about how gravity waves and large-scale waves together control the subsequent lifetime of TTL cirrus. And one reason can be observational when we want to really look at the whole lifetime of cirrus clouds, because thin TTL cirrus are difficult to observe. We know in situ observations are only sparse, and observing these thin cirrus from space can be challenging because they're optically very thin. But the recent Bicol observations from the STRATIL2 campaign have provided a unique view of these clouds. Indeed, there were long-duration superpressure balloons flying in the whole tropical belt, equipped with a LiDAR that sampled the tropical belt over several months and provided new observations of these thin cirrus clouds. So maybe you remember Thomas Lecine gave a presentation on this topic, I think a year ago in this journal club. And I'm just showing on this slide examples of their observations and a map of the flights where these observations took place. So one very interesting thing that these observations revealed is that thin cirrus are more ubiquitous than we previously thought. The LiDAR carried by the balloons being closer to the clouds, it showed a limit in the Calliope observations in terms of the optical depth that the satellite can observe. As circled in yellow on my slide, you can see that the optical depth below 2 × 10⁻³ are basically missed by the Calliope data. And more importantly for our study, BCool provided the first observational estimates of these thin cirrus cloud lifetimes that is represented on the right. You can see that it's a very skewed distribution with many short-lived clouds, but a non-negligible amount of long-lived cirrus that can dominate the cloud coverage. Okay, so we know that gravity waves typically fluctuate on timescales of minutes to hours, whereas large-scale tropical waves evolve over several days. And we know that thin cirrus lifetime lie in between these two regimes. So we first asked ourselves first, how do gravity waves alone and combined with the lower frequency waves can control cirrus lifetimes? Then, as I just showed, Lecine et al. Recently derived the first observational estimates of thin cirrus lifetimes. And I want to highlight the small fraction of long-lived clouds. It's the red bin on this figure. And explaining these longest-lived clouds can be very intriguing because they dominate the cumulative relative impact of the cloud population. So our second question is, can our simulations, taking into account the large-scale wave and gravity waves, can reproduce the observed population of long-lived TTL cirrus? And finally, we know that gravity wave activity is not uniform through the tropics. Some regions have stronger gravity wave activity, for example, as observed by the balloons and showed on my figure here with different momentum fluxes. So this raises a third question: how does gravity wave activity variability influence ice crystal formation and cloud persistence? And I will answer this question more in two different parts of my presentation because we assessed it with two different modeling techniques. So these are the three scientific questions that I will investigate today with you. And I'm starting with the first one that is assessed in a paper that we just submitted. Okay, so to address the cloud lifetime, we developed and used the LACED model. LACED stands for Lagrangian cloud evolution with dynamics, and it is specifically designed to follow the cloud evolution and investigate cloud lifetime statistics. It has an intermediate level of complexity between simple box model and more resolved cloud simulations. Indeed, we know LAST explicitly follows the evolution in height, size, and mass of a population of ice crystals in a Lagrangian frame inside a column, in blue on my slide. More precisely, we gather several crystals under the denomination of SIP. Each SIP is initialized at the top of the column, as you can see on my little schematic, in an initial cloud layer. And then they can grow by vapor deposition, shrink by sublimation, and sediment at their own fall speed in this saturated column. At the same time, the model remains intentionally simple. The column is an homogeneous environment. It does not represent any vertical variability. And finally, the microphysics are driven by a prescribed dynamic forcing that I circled in orange, and that can combine stochastic gravity wave variability and an idealized low frequency wave component. So we wanted to constrain our simulations as much as we could with observations. To start, the initial cloud layer and initial conditions are directly constrained by these LiDAR Be Cool observations. We focused on the thinnest TTL cirrus observed during the campaign with a small optical depth that I highlighted in yellow on this table, and which represent roughly half of the TTL cirrus observations. These clouds are typically, as you can see, at 17 kilometers of altitude, and we use the observed temperature and pressure in these conditions for our domain. And then the observed cloud depth, as you can see, is around 440 meters on average. And so that determines the average thickness of the saturated column in blue in my previous slide, as we know that usually clouds live inside saturated areas. So from these observations, we also prescribed the initial cloud characteristics. To go very briefly, we use the optical extinction seen by Be Cool. We use the extinction equation, and we infer an equivalent ice crystal population, assuming an initial mean radius of around 4 microns. So this figure on my slide is showing the distribution of observed extinctions in blue and our corresponding initial ice crystal population in green. So that was to describe our model and the initial conditions. And moving on to the dynamical forcing that we input in our model. Again, we want to use observations, and we represent it based on some balloon observations that happened during the STRATEOL2 campaign. So I represent here the flights of the balloons because I keep talking about this campaign, but you can look at the flights here. As you can see, they gave observations of the dynamics in the whole tropical belt. So for the low frequency forcing, we decided to create a very simple sinusoid that is constrained by observations of an inertia gravity wave. Indeed, the radio occultation instrument aboard the balloon flight revealed coherent fluctuations of several kelvins that lasted several days, as you can see on the upper part of this figure here. So these variations are associated with an inertia gravity wave, as the analysis in KO et al. 2026 has showed. And small parenthesis, this paper is very nice because it also highlighted that the cirrus cloud was observed being trapped inside the cold phase of this wave. In the lower panel, you can see the cirrus observed by Be Cool basically in the cooler phase of the wave. So we decided to represent this low frequency variability using an idealized sinusoidal forcing with a similar period of 4 days and the same amplitude. And we will investigate 4 possible initial phases, noted phi on my figure, and corresponding to different evolutions of vertical wind. So for example, for phi equals 0, it's the beginning of the cooling, so the vertical wind is 0 and is increasing. And for phi equals 3 pi over 2, it starts at the peak of the warming, and so the negative vertical wind speed starts decelerating at the beginning of the simulation. So the objective here is not to reproduce a particular wave event, but to see how the slowly varying temperature background can affect the cloud persistence. So in addition to the slowly varying large-scale wave, we know that TTL cirrus experience rapid fluctuations associated with gravity waves. The balloon observations illustrated how ubiquitous these fluctuations are. On the left, you can see a time series of gravity wave-driven vertical temperature, recorded by a balloon. But as we want to run tens of thousands of simulations, sampling directly from the observed time series does not necessarily give enough data. And so we first use a statistical parameterization developed by Karcher and Podlaja in 2019. It is represented in the middle of my slides, and I will not describe here the details of this parameterization. I just want to say that it reproduces the observed distribution of vertical velocities of Strateol 2 in the TTL. So the model experiences a somewhat realistic sequence of random cooling and warming events that are representative of some TTL conditions. Okay, so this was the method, how we want to assess these clouds' lifetime and characteristics. And I will present my results in 2 different parts. First, we will only use the gravity waves, and we will look at the evolution of the cloud characteristics depending on the age of the cloud. We will look at some sensitivity tests. And then we will add the low frequency wave, look at the impact on the lifetimes, and we will compare our lifetime statistics with Lecine et al. Observations. So I wanted to start this part by showing you a study case of a particularly long-lived cirrus cloud in our simulations. So as you can see, the cloud survived for about 44 hours under gravity wave forcing alone. Here I show in the middle panel the evolution of ice crystal size with time being the y-axis. During the first 15 to 20 hours, the gravity wave fluctuations induce an overall supersaturation, not much, as you can see by the ice supersaturation that is represented in purple. So it's a very small saturation, not much. And it still results in a growth of the crystals that can grow from around 4 to 8 microns. I'm showing you also the cumulative ice loss on the left part of my slide. You can notice that sublimation and sedimentation behave very differently. Sublimation occurs in abrupt jumps corresponding to episodic warming events, when sedimentation increases gradually because of the crystals that keep growing and falling. So you can see at 18 hours around here that we have a relatively strong warming event that almost completely dissipates the cloud. And we have a sudden increase in the sublimation, as you can see. However, a small portion of crystals manage to survive and grow back. And when it reaches a size big enough, basically the crystals are getting harder to be sublimated. So the cloud enters this stabilization regime where sublimation becomes much less likely. And the evolution of the cloud primarily evolves through slow sedimentation, as you can see on the left panel. So at the end, this cloud is just terminated by the sedimentation of the ice crystals. Moving on from this study case to statistics from our entire 50,000 simulations, we can first look at the left panel that shows the evolution of the mean crystal radius as a function of cloud age. We see first a very rapid increase in crystal size during the first few hours from around 4 microns initially to 8 microns again. And then it plateaus at around 8 microns. And this plateau reflects the balance that I wanted to say earlier between two competing processes that are, in our understanding, characteristic of our stabilization regime. You have at the same time cooling fluctuations from the gravity waves that promotes some deposition growth, and at the same time warming fluctuations that regularly erode the crystals and prevent unlimited growth and sedimentation that goes too fast. So there is this sweet spot where the crystals are big enough to not be sublimated very fast, but they don't grow too fast either. So while the mean crystal size reaches a plateau, as you can see, the cloud thickness continues to increase with age, obviously, as you can see on the right panel, as the sedimentation progressively broadens the cloud. So far, we've seen that this cloud evolution is initially controlled by the competition between growth and complete sublimation. But another very important parameter that can influence the cloud lifetime, of course, is the depth of this surrounded ice saturated layer. Remember this blue column, homogeneous column that we represent? So this determines how far ice crystals can sediment while remaining in saturated conditions. And so obviously that will affect the lifetime. So we varied this parameter in our simulations as the Be Cool observations found different depth, thickness of clouds. We also vary this parameter. And you can see the distribution of this parameter over our 50,000 simulations on the left panel. The middle scatter plot shows you the cloud lifetime as a function of the initial saturated layer depth. The color indicates the fraction of ice lost by sublimation. And as you can see, many short-lived clouds, so the ones that are more on the left part of this scatter plot, terminate from sublimation in yellow and occur across the whole range of depth of this saturated column. So in other words, whether this column is shallow or not doesn't really influence how quickly these clouds dissipate. But the picture changes for all the clouds. It's highlighted by my blue line. When the cloud age increase, the distribution shifts towards larger saturated layer depth. The longest lived clouds are on average found in deeper saturated columns. So this dependence only emerges when sedimentation becomes the dominant loss process. Last, we wanted to question whether this stabilization mechanism is changing if we change environmental conditions and gravity wave activity. So I'm showing here just lifetimes for different sensitivity test scenarios. Base is the scenario I just showed. Temperature, we changed the background temperature. The size, we changed the average or the mean initial ice crystal radius. And then geo, ocean, and continent test different gravity wave activity. Ocean is for a quieter environment, so less strong gravity wave fluctuations. And continental is the reverse, more active. And this was based on the Stratiol 2 observations. So the strongest sensitivity, as you can see, is really to temperature. In colder TTL conditions, clouds live roughly twice as long as in the base case, and conversely for warmer conditions. For the crystal size, we can understand easily that larger crystals are more resistant to complete sublimation from the gravity waves, and so they can survive longer. And finally, for the different environments, gravity wave environment conditions, we find this interesting effect that when we have stronger gravity wave activity, it shifts the equilibrium crystal size towards larger values. I don't know if you remember, it was around 8 microns. We find the value a little bit more. And the next effect is a reduction of the cloud lifetime in more active regions. Okay, so now we can add our low frequency forcing. So I'm showing on the right part of my slides these box plots of lifetimes. By the way, I'm sorry, I didn't say it. It's from Q10 to Q90. The average, I think, is the dot, and the median is the bar. So I'm showing with the low frequency only on the right panel and the gravity wave plus low frequency in the left panel. So without the gravity waves, we can see that the low frequency wave produces a very phase-dependent behavior. If the cloud initialized during the cooling phase, it will live longer. If it's initialized during the warming phase, it will rapidly sublimate. But when the gravity waves are added and we have this superposition of the two, you can see that the lifetime distribution is actually broadened and shifted a bit towards the shorter lifetimes. We understand that gravity wave induced sublimation can happen even during the low frequency cooling phase. And on the other hand, cooling fluctuations from gravity waves can help the clouds grow and stabilize, even if we're in the initial warming from the low frequency phase. Very quickly, if I give you an example, for phi equals 0, the low frequency cooling is initially weak, as we mentioned. So the gravity wave induced warming event can counteract it quite easily. Whereas if we go to phi is equal pi over 2, we start with a stronger cooling. And so the overall result gives the longest lifetime when we start with a strong cooling from the low frequency wave and when we add the gravity waves, as you can see by this box plot here. Okay, so this was answering my first question about how gravity waves alone and gravity waves plus or low frequency wave can affect the cloud persistence. And now we are moving to the second question. Can we reproduce the longest lived clouds in our simulations, the ones that are observed by the BCool observations? So here I compare my simulated lifetimes with the BCool observations, and I want to highlight that this comparison is very first order because we are comparing like apparent lifetime from balloon observations that are somewhat Lagrangian with our model that is looking in a Lagrangian way. So, it's let's be a bit careful with this comparison. But anyway, so this figure shows in dashed line the lifetime from Lecine et al. The blue line corresponds to our simulated results, including all phase from the low frequency forcing, so all the phi that we talked about, and the gravity waves. And then the stacked bins are more of a detail. I just wanted to detail the distribution when we take into account the gravity waves and only the cold phase of the low frequency forcing, because we know that these clouds are mostly found in the cold phase of large scale waves. So this motivates our choice. So both our simulations and observations have a larger portion of clouds lasting less than 6 hours than more. And both the observations and simulation represent a non-negligible part of clouds that last more than 12 hours. This small, long-lived population is important because it contributes to around 22% of the total cloud coverage, as you can see on my table. And this agrees with the observational idea that the rare long-lived cirrus can have a disproportionate relative impact. Finally, the stacked bins show this process decomposition. You can see that the short lifetimes are mostly sublimation dominated, as we talked about a few slides before, while longer lifetimes occur when crystals grow enough to survive warming events, and they are largely lost by sedimentation. So if I want to conclude on these two first questions with just 4 key points, we found that the cirrus lifetime emerges from a competition between rapid sublimation and gradual sedimentation. We found that gravity waves can maintain a little bit the cirrus through this stabilization regime, but at the end of the day, rare warming events can just abruptly terminate the cloud and overall shortens the cloud lifetime. Low frequency waves control whether the environment favors growth or rapid sublimation. And we found that our model reproduced a skewed Be-Cool lifetime distribution, included these rare long-lived cirrus clouds. Okay, and I can move on to my last part of this presentation. So you might have noticed that in the first parts, the impact of the waves on nucleation was omitted. We had an initialized crystal population. And so now we're focusing on the impact of this gravity wave variability on homogeneous nucleation of ice crystals. And I'm presenting here the results of the paper led by Eric. Again, this study is using observations of gravity waves from the superpressure balloons. I'm just showing you here the flights of the balloons to refresh your memory. The only thing I want to point out is that we had 2 types of balloons, STR and TTL, that were flying at 20 and 18 kilometers of altitude. So the first step to investigate the gravity wave activity variability was to divide the observations in time series of 5-day segments, which are long enough to get robust wave statistics, but short enough to capture changes in the dynamical environment. So I show here distributions of the standard deviation of vertical wind and of temperature for all these segments. And as you can see, we observe a broad range of gravity wave amplitudes in the tropical tropopause region, which really matters for cirrus formation because we know homogeneous freezing is very sensitive to cooling rates. So this kind of motivated our study. The second step was to feed these 5-day time series segment, of which you can see the vertical velocity distributions on the left, onto 0D, like box model, karma simulations. We just look at the impact on the nucleation. So you can see that the observed variability in gravity wave activity is large enough to produce quite substantial variability in homogeneous freezing. Depending on which 5-day segment we used, the mean ice number concentration ranges from 0.8 to 4.9 per centimeter cube. So that was the first result, but we wanted to go a little bit further in investigating the gravity wave activity variability, and we decided to link it to the distance to their convective source. We know that convection is a primary source of gravity waves in the tropical band. And so on the left, I'm showing this standard deviation of vertical velocity as a function of distance from convection. You can see how it decreased kind of steep in the first 200 kilometers. So the gravity wave activity is stronger close to convection. And then the right panel is a bit trickier. It shows more the spectral content of the wave field that we observe as a function of distance to convection. More precisely, I'm showing ratios of momentum fluxes, basically higher frequency momentum fluxes over all frequency momentum fluxes that we observe. The key message of this figure is just to say that the relative contribution of the higher frequency waves to the total observed momentum flux diminishes the further we get from convection, meaning that the spectrum of waves changes with distance to convection and can't be just represented with one mean slope. And also, the higher frequency waves are not observed everywhere. So we decided to investigate what would be the impact of omitting the highest frequency waves onto homogeneous nucleation. So we used again this KP19 parameterization that I described a little bit earlier, because we can easily select frequencies that we want to represent. Panel A shows the impact of varying the maximum wave frequency. When we have more high frequency waves retained, the distribution of vertical velocities becomes broader. So they are carrying more of the highest vertical velocities. Panel B shows that including more high frequency variability shifts a little bit the number concentration distributions towards higher values. And panel C summarizes this result as the frequency increases, both sigma W and the mean ice number concentration can increase. But what would happen if we keep the sigma W constant? So we tried to test whether same distributions produced by different wave frequency intervals, by different wave spectrum, can give similar nucleation results. This is important as gravity wave parameterizations usually try to reproduce just the vertical velocity distribution. So the left figure compares different vertical velocity distributions. The black curve is our reference case. It's not exactly what we're interested in. We want to look at the red and green curve. As you can see, they have the same sigma W, very similar distribution, but one has all frequency retained, but with smaller amplitudes, and the other one just got the highest frequency removed. On the right, you can see the effect on the homogeneous freezing. You can see that the resulting red and green curves are quite different. Even though the red case includes the higher frequency waves, it now produces fewer crystals than the green case. So higher frequency waves are associated with large vertical velocities, as we just saw, strong cooling rates, yes, but it can also lead to less efficient nucleation. We wanted to investigate why, and we looked at the vertical winds happening at the nucleation. We know homogeneous freezing needs some cooling, but it also needs this cooling to last long enough. If the fluctuation reverses too quickly, the air parcel can start warming before the nucleation can fully develop, and it is called the quenching of the nucleation. So the question we asked is, during a nucleation, how often does the vertical wind reverse from positive to negative? So in this histogram, the dashed vertical line marks the 0 vertical velocity. Values on the right correspond to the cooling, values on the left to the warming. And again, the green curve corresponds to where we remove the highest frequencies, and the red curve keeps all the frequencies. So when the highest frequencies are present, we found that nucleation events are more frequently quenched. For weak nucleation events, what's my distribution show here? 94% of events are quenched when we have the highest frequency included, when there are only 41% when we remove the highest frequencies. We also showed that these quenched events mainly populate the lowest crystal number part of the distribution that we find. So overall, we found that the highest frequency waves can at the same time increase the cooling rates, but they can also shorten the cooling duration and increase quenching of the nucleation. So to conclude this last part, and this is my last slide, we found that observed TTL gravity wave forcing is highly variable in amplitude and environment. High frequency waves dominate the strongest updraft and the highest nucleated ice concentration, but at the same time, it can lower nucleation through quenching. And we found that the same sigma W does not necessarily imply the same nucleation response, and the wave spectrum, which frequency represents, really matters. And that's it for my presentation, and thank you for your attention.